Ever wondered how a computer system efficiently manages multiple operations simultaneously without confusion? The secret lies in a mechanism called interrupts. You see, interrupts are a bit like an alarm bell in a computer system. When something urgent crops up, the normal flow of program execution is temporarily suspended, allowing a specific task to be performed. Think of it as a teacher in a classroom. While the teacher is giving a lecture, a student raises their hand with a question. The teacher interrupts the lecture to answer the question before resuming the lecture. Similarly, in the world of computing, interrupts handle events that require immediate attention, such as hardware events, external signals, or exceptional conditions. When an interrupt occurs, the processor halts its current task and diverts to a special piece of code, an interrupt service routine or interrupt handler, to deal with the situation. So in essence, interrupts are the traffic cops of the computer system, ensuring each task gets its turn in the spotlight. Interrupts come in different flavors, each with its unique characteristics and uses. Let's dive into the 4 main types of interrupts: hardware interrupts, software interrupts, maskable interrupts, and non-maskable interrupts, or NMIs for short. First up, we have hardware interrupts. These are triggered by external hardware devices or peripherals to signal events that require attention. For instance, a printer might send a hardware interrupt to let the system know it's finished printing a document, or a network card might do the same to signal the arrival of new data. Next, we have software interrupts. These are generated by software or programs to request specific services from the operating system. Say, for example, a program wants to read a file or send data over the network. Instead of doing this directly, it will generate a software interrupt to request the operating system to perform these tasks on its behalf. Then we have maskable interrupts. These can be disabled or masked by the programmer to prevent their immediate response. This can be useful in situations where we need to ensure that a certain piece of code runs without being interrupted. For example, when writing data to a hard drive, we might want to mask interrupts to ensure that the data is written correctly and completely before any other task is handled. And finally, we have non-maskable interrupts or NMIs. These cannot be disabled by the programmer and are often used for critical events. Think of situations like hardware faults or power failures. In these cases, it's crucial that the interrupt is handled immediately, no matter what else is happening in the system. So there you have it. Hardware interrupts, software interrupts, maskable interrupts, and non-maskable interrupts. Each type serves a specific purpose, and together, they allow a computer system to handle an array of tasks concurrently and efficiently. Understanding these types helps us appreciate how versatile and flexible the interrupt mechanism is. Stay tuned for the next scene where we'll delve into the interrupt handling process. But how does a system handle an interrupt? The process is not as complicated as you might think. Let's dive into the intricacies of the interrupt handling process, which can be broken down into 7 key steps. First up, we have the interrupt request, or IRQ for short. This is where it all begins. An external device or internal event triggers an interrupt request, essentially waving a virtual flag to signal that something noteworthy has occurred that requires immediate attention. Next in line, we have the interrupt controller. Picture this as an air traffic controller for interrupts. Its job is to manage and prioritize multiple interrupt requests, ensuring that the most urgent ones are dealt with first. Following the interrupt controller is the interrupt vector. This is not a space-age term, but rather a unique address associated with each interrupt. Think of it as a map that points the processor to the corresponding interrupt service routine, or ISR. The 4th step is the context switch. This is where the processor takes a moment to save the current state of the interrupted program, a process also known as storing the context. It's like hitting pause on a movie, ensuring that you can pick up right where you left off. Now we come to the heart of the process, the interrupt service routine, or ISR. The ISR is a dedicated piece of code that tackles the specific task associated with the interrupt. It's the firefighter who puts out the fire, the medic who tends to the wound. It may interact with the operating system, perform necessary actions, and generally handle whatever the interrupt was signaling. The 6th step is the return from interrupt, or RTI. Once the ISR has completed its task, control is handed back to the interrupted program. It's the equivalent of hitting play on that paused movie, resuming right where we left off. The processor restores the saved context, and it's as if the interruption never happened. The final step is a bit of a housekeeping task. The interrupt is acknowledged, and the interrupt controller is informed that the interrupt has been handled. This allows the controller to move on to the next interrupt in line. So there you have it. From the initial interrupt request to the final acknowledgement, that's the journey of an interrupt in a nutshell. Each step plays a crucial role in ensuring that the system can manage a variety of tasks concurrently and efficiently. And remember, while the process may seem complex, it all happens in the blink of an eye, allowing our computers to multitask and handle unexpected events with grace and speed. This sequence ensures that the computer can handle any interruption smoothly and efficiently. Now let's dive into some real-world examples of interrupts. First up, we have timer interrupts. These are generated by a timer or a clock within the computer system. Imagine a cooking timer that buzzes when the set time is up. In a similar way, the computer's internal clock sends out a timer interrupt when a specified time period has elapsed. This is especially useful for scheduling periodic tasks, like refreshing the screen display or updating system time. Next, we have I/O interrupts. These are triggered by input and output devices such as a keyboard, mouse, or printer when they need attention or when a data transfer is complete. For instance, when you press a key on your keyboard, it sends an I/O interrupt to the processor, signaling that it has new data to process. This allows the processor to carry on with other tasks until the keyboard has something for it, thus improving efficiency. Then, there are exception interrupts. These are a bit more dramatic as they're generated in response to exceptional conditions, such as a divide by zero error or a page fault. These interrupts prompt the processor to pause the current program, handle the exception, and then decide whether it's safe to continue with the program or if it needs to be terminated to prevent further issues. Finally, we come to system calls, which are software interrupts initiated by programs to request services from the operating system. When a program needs to access resources or perform operations that require special privileges, it can't just go ahead and do it. It must make a system call, which triggers a software interrupt, and the operating system takes over to safely carry out the request. So whether it's the rhythmic ticking of a timer, the click of a keyboard, an unexpected error, or a polite request for service, interrupts are constantly at work, making sure everything runs smoothly and efficiently on your computer. These examples illustrate how interrupts weave into the fabric of our daily computing experience. Interrupts are more than just a fancy computer term. They are the backbone of efficient computing. Let's revisit the key points we've unpacked in our journey through the world of interrupts. We explored the types of interrupts. Remember, hardware interrupts are triggered by external devices or peripherals, while software interrupts are generated by programs to request services from the operating system. We also talked about maskable and non-maskable interrupts. Maskable interrupts can be disabled to prevent immediate response, while non-maskable interrupts, often used for critical events, cannot be disabled. Then we delved into the interrupt handling process. It starts with an interrupt request, followed by the interrupt controller managing and prioritizing multiple requests. Each interrupt is associated with a unique interrupt vector, leading to a context switch where the processor saves the current state of the interrupted program and jumps to the interrupt service routine. The interrupt service routine, or ISR, handles the specific task associated with the interrupt. After the ISR completes its task, control returns to the interrupted program and the saved context is restored. We also discussed some examples of interrupts like timer interrupts, I/O interrupts, exception interrupts, and system calls. Each has a specific purpose and contributes to the overall efficiency of the system. Finally, we highlighted the benefits of interrupts. They increase the efficiency of the system by allowing the processor to respond to events without wasting time repeatedly checking for them. Interrupts also enable real-time responsiveness, providing quick responses to time-sensitive events. Moreover, they foster modularity, as the system can handle different events independently through separate ISRs. In essence, interrupts are a fundamental aspect of computer architecture, playing a crucial role in the efficient functioning of modern computing systems. They ensure that the processor can handle a variety of events concurrently and efficiently, providing responsiveness and flexibility to the system. So, next time you marvel at your computer's multitasking prowess, remember to thank the humble interrupt for keeping everything running smoothly.